Hello students, in previous lecture we have studied about the packing efficiency of cubic unit type of unit cells, that is packing efficiency of simple cubic unit cell as well as packing efficiency of body centered cubic unit cell. Then we have already calculated the percentage of total volume occupied by the atoms in the unit cell. All of you have studied about the unit cell, number of atoms present in the unit cell and arrangement of the spheres or atoms or molecules or ions in the solid crystalline lattice, and those arrangements of spheres or atoms or molecules or ions is of different types, that we can arrange those spheres in one dimensional, two dimensional and as well as in three dimensional pattern. When we arrange the spheres in three dimensional pattern, that is on x axis, y axis and z axis, then that arrangement of the spheres in the crystal lattice, it results into formation of 14 different types of unit cells. All of you studied about that, and those 14 types of unit cell I have already discussed with you with the help of diagrams and figures. Then you may revise or remind those all 14 types of unit cells. Then in previous lecture I have already discussed about the percentage of that volume occupied by the spheres in cubic unit cell. First we will remind that packing efficiency of spheres in the cubic crystal unit cell. Then see here, packing efficiency of cubic type of unit cell, that is of simple cubic unit cell, body centered cubic unit cell and face centered cubic unit cell, or it is also known as CCP unit cell. Then first of all we have to remind that packing efficiency of those cubic unit cells. See here in the figure, in the chart given here in your textbook, observe the chart and we will remind again about the packing efficiency of those unit cells. See here in SCC type, that is simple cubic unit cell type of unit cell, the relationship between that edge length and radius of the sphere, all of you have studied about that, those spheres which having the radius r and the cubic unit cell in which the edge length of that cube or cubic unit cell is considered as a. As it is a cubic type, therefore all edges is of a length. All of you have studied about that. Then we have to remind the relationship between edge length and radius of the spheres, and those spheres are arranged at the corner of that unit cell as well as inside the body of that unit cell as well as at the all six faces of that unit cell. Then when in simple cubic unit cell, all of you have already studied about that, there is only one atom, isn't it? Then the relationship between radius of the sphere, that means radius of atom, and edge length of that unit cell is, that is r is equals to a upon 2. That means radius of the atom is half of the edge length of that unit cell. Then the volume of that atoms or particles which is occupied in the unit cell, that is, see here, pi a cube upon 6. Then see here, there is only one atom, therefore the volume of one atom or particle is pi a cube upon 6, and as that simple cubic unit cell, it contains only one particle, one atom, therefore total volume occupied by that one particle in unit cell. That means in unit cell, in SCC, only one particle is there, one atom is there. Therefore, the volume of one atom is the volume occupied by the particles in unit cell is also same. That is pi a cube upon 6. As well as, see here, in BCC type. In BCC type cubic unit cell, there are two particles are there, and relationship between radius of the sphere and edge length, that is r is equals to, see here in the chart, r is equals to root 3 a upon 4. As well as, see here, the volume of one particle in BCC type of unit cell is root 3 pi a cube upon 16. Then see here that root 3 pi a cube upon 16 is the volume of one particle in BCC, but there are two particles are there. Therefore, we have to calculate the volume of two particles in unit cell. Therefore, we have to multiply this by 2. Therefore, we get here the volume of two particles in BCC. Then in BCC, total volume of particles occupied in unit cell, that is root 3 pi a cube upon 8. See in the chart. Then one more type of unit cell is there, that is face centered cubic unit cell or CCP type unit cell. Then relationship between r and a, that is edge length, that is r is equals to root 2a upon 4, and the volume of one particle, that is pi a cube upon 12 upon root 2, that is pi a cube upon 12 into root 2. Therefore, there are in BCC 4 particles are there. Therefore, that is the volume of only one particle, and there are 4 particles. Therefore, we have to multiply it by 4. Therefore, here we get the volume of all particles occupied in the BCC type of unit cell, that is pi a cube 3 upon 3 root 2. See here in the chart. Then one more chart is there given in the textbook, which is related with the packing efficiency, that is percentage of the atoms occupied in one unit cell, and here as well as percentage of void present in that type of unit cell. Then see here one more chart is given here of the packing efficiency of simple cubic unit cell. See here in simple cubic unit cell, all of you have already studied about that. There is only one particle, one atom is there. Therefore, packing efficiency is 52.36%. All of you have calculated that percentage in previous lecture using the formula of packing efficiency. You may remind that lecture, or you may remind that concept from previous lecture. And as well as percentage of void means empty space, in SCC is 47.64%, because packing efficiency is 52.36. Therefore, the percentage of void is 100 minus 52.36. We get 47.64%. As well as in BCC, the packing efficiency of unit cell is 68%, and therefore void percentage of void is 100 minus 68, that is 32%. Because there are 2 atoms are there in BCC type of unit cell. As well as in FCC, there are 4 particles are there, 4 atoms are there. Therefore, packing efficiency increases in FCC, and FCC is more efficient because packing efficiency is greater in the face centered cubic unit cell of CCP, that is 74%, and percentage of void is 26%. Then one more relationship all of you have studied in previous lecture, that is there is the relationship between molar mass and density of the substance of that crystalline lattice structure and the age length of that unit cell. That is the relationship between rho and A. That is age length as well as capital M, that is molar mass of that given crystalline substance or metallic substance. That is here rho is equals to, see here, N into capital M upon A cube into Na. All of you have studied those all parameters. Then we will again remind those all parameters to study about that number of particles and unit cells in x gram of metallic crystals. Then see here, if any metallic crystal is given, it is of x gram. That means here mass of that crystalline substance is x gram. Then that x gram of metallic substance or crystal, it contains how many number of particles or atoms are there, as well as how many unit cells are in that x gram of metallic crystalline substance. We have to calculate it by using the formula of the relationship between rho and molar mass, that is density of that substance, molar mass of that substance, and age length of that substance. Then let us consider, that is here, let rho, that is the density of, it is a density of that substance, metallic substance or crystalline substance. N, that is number of particles. That means there are number of particles of that substance, metallic substance or crystalline substance. M is the molar mass of that substance. Molar mass of substance. And here A is the age length of unit cell. Age length of unit cell. Therefore, here volume of unit cell. Volume of unit cell is A cube, which is denoted by also V. That means volume of unit cell, cubic unit cell is A cube, because all sides of cubic unit cell is same, that is A. And whereas Na is nothing but it is a Avogadro number, that is 6.022 into 10 raised to 23 atoms, molecules or ions are there. Then using this formula we can calculate the number of particles, number of atoms, number of spheres, number of molecules or number of ions present in x gram of metallic crystal. Then here, if the mass of that crystalline substance is x gram, then we can calculate the number of particles as well as number of unit cell present in it. Then all of you have studied about that. What is rho, n, small n, A age length, A cube is the volume of that unit cell, rho is the density of metallic substance, m is the molar mass of that substance. Therefore, we get the formula, that is rho is equals to n into m upon A cube into Na. Then see here, if there is x gram of metal is given, that is crystalline substance is of x gram, then we can calculate the number of particles, number of spheres, number of particles or number of spheres in x gram metallic crystal. Therefore, here we can calculate the number of particles or number of atoms present in x gram of metallic crystal. All of you have studied that m is the molar mass of that substance. Then according to that mole concept, if M is the molar mass of substance which contains about Na particles. Number of particles, that is Na. That means there are, if m gram of that crystalline substance, m gram of metal or metallic crystal which contains 6.022 into 10 raised to 23 particles, and therefore we can calculate the number of particles present in x gram of metal which contains, see here, that Na particles are there. Therefore x gram of metal, it contains x into Na upon m particles are there. How many particles are there? See here, if m gram of metal contains Na particles, number of particles is Na, therefore x gram of metal contains x into Na upon m. Then we get that much number of particles present in x gram of metal. Then we can substitute the value of m in this equation. Therefore here we have to get the value of m. Therefore we can convert this. Therefore here m, capital M, is equals to rho into a cube into Na upon m. Therefore putting the value of m in this formula, therefore here we get number of particles, atoms in x gram metal is equals to, see here, that is x into Na upon m. See here, the value of m, we will using that value of m in this equation. Therefore rho into a cube into Na upon m. Then simplifying this, we get x into Na particles upon rho into a cube into Na into n. Then we here Na get cancelled. Therefore here we get the formula, that is x into n upon rho into a cube. That much particles present in x gram metal. Then see here, we get the formula to calculate the number of particles present in x gram of metal, as well as we can calculate the number of unit cells in x gram metal. Then number of unit cell in x gram metal. To calculate this, we can remind that if there are n particles present in one unit cell, then see here, there are n particles present in one unit cell. Then see here, there are total that much particles are present in x gram of metal. Then x gram metal contains that much particles, that is xn upon rho into a cube particles are there. See here, xn upon rho into a cube particles contains how much unit cells are there. See here, there are total n number of particles are there. Then if there are n particles are there, then that n particles present in 1 unit cells, isn't it? If it is of SCC type, then there is only 1 unit cell. If it is BCC type, then there are 2 atoms are there or 2 particles are there. If it is FCC type or CCP type, then there are 4 particles are there. Therefore, here in x gram of metal, how many particles are there? Xn upon rho into a cube particles are there. If n particles means 1 unit cell, that means n particles present in 1 unit cell. Therefore, Xn upon rho a cube particles are present in how many unit cells? Then we have to calculate this. Then see here Xn upon rho into a cube into 1 upon n. Therefore, here number of unit cells is equals to, see here Xn upon rho into a cube into 1 upon n. Upon n means 1 upon n. Therefore, here n get cancelled and here we get x upon rho into a cube. Then see here number of unit cells present in the x gram of metal which contains x upon rho into a cube unit cells are there. Then all of you have studied about that volume is equals to, that is see here rho is equals to mass upon volume. Rho, that is density, is equals to mass upon volume. Therefore, here mass is x gram and here volume is v. Therefore, rho is equals to x upon v. Therefore, here we get v is equals to, therefore v is equals to, see here x upon rho. Then we can calculate number of unit cell in v dm cube of metal. That means if there are volume of that metal is v dm cube, then how many number of unit cells are there? Then we get the number of particles present in v dm cube of, if there is mass of the metal is not given, if volume of that metal is given, then we can calculate that number of unit cell present in v volume, v dm cube of metal. That is, say here it is v upon a cube. We get here v upon a cube because here we x upon rho, here x upon rho, that is here we get x upon rho into a cube. But here, see here x upon rho means here v is there, x upon rho, that is v is there. Therefore, here we get v upon a cube particles are there. That is the relationship between, that is number of particles present in x gram of metal, number of unit cell present in x gram of metal, crystalline substance, as well as number of unit cell present in v dm cube of metal. And here few numerical examples which is given in the textbook. We will solve those numerical examples which is based on those formulas which shows the relationship between number of atoms as well as number of unit cells present in x gram of metal or present in v volume of crystalline metal. Then see here one of the example given here, that is niobium forms BCC structure, then the density of niobium is 8.55 gram per cm and age length of that unit cell is 330.6 pm, that is picometer. How many atoms and unit cells are present in 0.5 gram of niobium? Then read that example again and again, and first of all write the given parameters or given values in the example. Observe that or read that example and you may find out that here x is equals to, x means here that is mass of that niobium substance. X is given here, that is 0.5 gram. 0.5 gram substance is given here. Then here the structure of that niobium. Here BCC type of unit cell is there. BCC type of unit cell is there. Therefore, there are total number of atoms are 2. All of you studied about that. Therefore, n is equals to 2. And here density is also given. That is the value of rho. That is density of niobium is 8.55 gram per cm cube. Then see here units of those are in same CGS unit or CGS system. As well as there are age length of that unit cell is also given. Therefore, here A is equals to 330.6 pm. Then the age length which is given in picometer or it may be given in nanometer. Then we have to convert that picometer or nanometer into centimeter because here CGS units are given here. Therefore, here 3.30.6 pm, that is picometer, which can be converted into centimeter, that is 3.306 into 10 raised to minus 8 centimeter. That means here age length which is given. That then we can calculate the number of atoms or particles. Then how many atoms are there and how many unit cells are present in that much gram of niobium, 0.5 gram of niobium. Then number of atoms in 0.5 gram of niobium. That is here we have to use the formula which we have already calculated or which we have already proved that here. Therefore, here XN upon rho into A cube. Using this formula, we can calculate the number of atoms present in 0.5 gram of niobium. Then putting the values of Cn(x), that is 0.5 into n, that is number of particles is 2 upon rho, that is given here 8.55 into here A, that is A cube here. Therefore, here 3.306 into 10 raised to minus 8 bracket cube, because here the value of A, that is 3.306 into 10 raised to minus 8 centimeter, and here A cube is there. Therefore, if we have to calculate this all, then by simplifying here, then we get the value, that is 3.25 into 10 raised to 21 atoms are there. Atoms are there here. That means number of atoms present in 0.5 gram of niobium, that is 3.25 into 10 raised to 21 atoms. You may solve this formula using or example using log table. Then we have to calculate the number of unit cell in 0.5 gram of niobium. That is the total number of atoms present in it that we have calculated, that is 3.25 into 10 raised to 21 atoms. Then if we have to divide that by n, that is number of n particles, then we can get the value, that is of number of unit cells. If there are n particles, then here there are 2 particles are there in niobium, BCC type of niobium. Therefore we have to use the formula, that is x upon rho into a cube. Therefore putting the values of all these, then we can calculate that here we get the answer. Or if we have to divide this by number of atoms, that is by 2, therefore here we get the value, that is 1.675 into 10 raised to 21 unit cells are there. Then here we get the number of unit cells present in 0.5 gram of niobium, as well as number of atoms present in 0.5 gram of niobium. As well as one more example which is given here. See here, a compound forms HCP structure. Then see here, there are HCP structure is given here, that means hexagonal closed packed structure of that compound is given here. What is the number of octahedral voids and tetrahedral voids, as well as total voids in 0.4 mole of it. Then all of you have studied about that. See here, first we have to write that total number of moles, that is number of moles is given here 0.4 moles. But all of you have studied about that according to the mole concept. 1 mole consists of, 1 mole means there are 6.022 into 10 raised to 23 particles are there, or atoms are there. Atoms are there. And here how many moles are given? 0.4 moles are given here. Therefore that 0.4 moles contains 0.4 into 6.022 into 10 raised to 23 atoms are there. If we have to multiply this, then we can get the value, that is 2.4098 into 10 raised to 23 atoms are there in 0.4 mole of that compound, HCP type of compound. And all of you have studied that one formula, that is number of atoms is equals to number of, that is octahedral voids are there. That means here the number of atoms present in unit cell is the number of octahedral voids. Therefore there are how many octahedral voids are there? 2.4098 into 10 raised to 23 octahedral voids are there. Therefore here 2.4098 into 10 raised to 23 octahedral voids are there. Octahedral voids. And all of you have studied that there are double the tetrahedral voids than the octahedral voids of number of atoms. Therefore there are number of tetrahedral voids is equals to 2 into, that is 2.4098 into 10 raised to 23. Therefore here we get 4.818 into 10 raised to 23. That means here we get the tetrahedral number of tetrahedral wires as well as number of octahedral wires, and if we add both the number of tetrahedral wires as well as the number of octahedral wires, then here the addition of these two, then we get there are total 7.22. That is here if we add those both, that is 2.4098 into 10 raised to 23 plus 4.818 into 10 raised to 23. Then here we get 7.22, that is 7 into 10 raised to 23. Total voids are there. Total voids are there. Then that is about the numerical examples which shows the relationship between number of particles and number of unit cells present in the X gram of crystalline metal lattice. Then we will study about the few new concepts which is related with the metallic crystals or crystalline substances in the next lecture. Thank you.